So in section 2.2, as you can read here, we're going to be looking at limits of functions and sequences. And as we saw in chapter 1, actually relating the two, there's a strong relationship that exists between limits of sequences and limits of functions. All right, so now we're going to be looking at those relationships in this section. So when we have the definition of a limit, we're saying we can make x's get arbitrarily close to x naught, which make this epsilon, I guess, tube or neighborhood of L arbitrarily small, so that those values get arbitrarily close to L, right? So that was the definition of the limit that we used a bunch last time. And now the question is, if I have a sequence x of n that goes to x naught, do we have a sequence then of fxn that go to L? Right, so like I said with intuition, this gets arbitrarily close to x naught, so then maybe this these values get arbitrarily close to L. We do have a theorem that says let f be the function from D to R, that maps D to R, with x naught an accumulation point of D, then f has a limit at x naught if and only if for each sequence x of n converging to x naught, with x of n being points in D, and xn not being equal to x naught for all n, the sequence f x of n converges. So the answer to the question in the previous slide is yes, we do converge to L. So the proof is quite long actually, but it shouldn't be too hard to follow, and especially because it's biconditional, that's why we have that length. But first we're going to suppose f has a limit L at x naught. We're going to let xn be a sequence of members of D distinct from x naught but converging to x naught. And we're going to consider the sequence f of xn. Well, we're going to choose an epsilon greater than 0, right? Well, with that epsilon greater than 0, there's a delta greater than 0 such that if the distance between x and x naught is less than delta, well, then the difference between f of x and our limit point is less than epsilon. Right, and this is just coming from the fact that f has a limit at x naught. Well, since x of n is converging to x naught, there's an n such that the difference between xn minus x naught is less than delta. Right, that's just definition of convergence. We learned that last chapter. Okay, so now for n greater than or equal to n, we have that x of n minus x naught is less than delta, and x is an element of D. Well, if that's true, then f of xn minus L should be less than epsilon. And what does this tell us here? Well, if that sequence of functions is the difference is getting arbitrarily small, it's less than epsilon, then this sequence converges and it converges to L. So that's one direction. Next direction is we're going to suppose that the latter condition is satisfied, so all the sequences f of xn have a common limit, and we're going to call that limit L. And suppose that L is not a limit of f at x naught. Well, then there's an epsilon greater than 0, such that for every delta greater than 0, there's an x in D with the difference between x and x naught being less than delta, such that the limit, the difference between the function at x and the limit is greater than or equal to epsilon. Right, so we're basically saying that L is not a limit because of this here. Because f of x minus L is greater than or equal to epsilon. Right, so we're kind of negating the definition of a limit to show that L is not a limit of f at x naught, right? So, in particular, for each positive integer n, there is an xn in D with xn minus x naught less than 1 over n, such that f of xn, this sequence function minus L, is greater than or equal to epsilon. Well, this sequence, x of n, converges to x naught. And it's a sequence of members of D distinct from x naught. Therefore, f of xn must converge to L. Well, then that contradicts this fact here. Therefore, L must be a limit of f, right? So we assumed this first, and we reached a contradiction. Therefore, this must hold. And that proves our biconditional proof. This is the longest proof we'll have. This will be actually a short section. And well, here's the picture for it. Right, if we have a sequence xn converging to x naught, then f of xn must converge to L. Okay, next thing, observation. We're going to let f be a function that maps 0, 1, the open interval, to the real numbers. Well, here we're going to note that there's a k greater than 0, such that for all x, y in 0, 1, this inequality holds. Right, we can always find a number k such that that inequality holds no matter how big. So we move on to the next theorem. Well, before we even go on to the next theorem, the previous theorem says let f map D to R, and suppose x naught is an accumulation point of D. If for each sequence x of n converging to x naught, if for each sequence x sub n converging to x naught, the sequence f of x sub n is Cauchy, well then f has a limit at x naught. And we do that by using, well, we see it by using this up here. That's why I brought up the observation. But now we're going to shift through our newly gained knowledge of sequences and discover theorems concerning limits of functions. And many of these theorems can be proved by just exploiting a previous theorem, right? The first theorem we proved. But in some cases, we will I'll give a direct proof in order to introduce, that act of finding that clever delta. But this next theorem says let f map D to R with x naught an accumulation point of D. If f has a limit at x naught, then there's a neighborhood Q of x naught and the real number m, such that for all x in the intersection of Q and D, f of x is bounded by m. The absolute value is bounded by m. So again, I'm just going to have the picture here to help illustrate what's going on with the proof. So in this case, we're going to let epsilon be equal to 1. So this is L plus 1, and this is L minus 1. And let L be the limit of f at x naught. Well, there's a delta greater than 0, such that the difference, so this here, I'm going to do it in green, such that between these 2 points, we have that the difference between f of x minus L is less than epsilon. Right, so it's exactly what this is showing, that between this here and this over here, this line over here, our points lie within here of L, right? Lie within epsilon, or in this case, 1. So if x is in D, and D here is this over here. This is D. Or if x of x naught is in D, we're going to define M to be the maximum of L minus 1, L plus 1, and f of x naught. So when would the max be L plus 1? Well, in this function here, this is the greatest point, or the biggest. So in this case, our max here would be L plus 1. But say we were in the negative y values, and maybe our function, actually, no, we can do one here. Say our function was something like no, I take that back. Okay, let's go to the y values, the negative y values. Well then, this should be L plus 1, let's say, and this is L, and then down here would be L minus 1. Well, the least is L minus 1, but because we're taking the absolute value, that'd be the greatest, so that's when we would set the max equal to L minus 1. And when we would set the max to f of x naught as our max is, if we take a look at this function here, maybe f of x naught is defined up here, right? Because this hole, there's a hole there. So maybe f of x naught is bigger than all these values of the function in these places, right? These places, because it's all the way up here. That's when f of x naught would be the max. But anyway, whatever the case may be, we choose M to be the max of those 3 values. What does that tell us? Oh, this is saying if x is in D, right? So if this point, sorry, let me erase to make this clear. So this here I'm going to underline in green. If f of x naught is defined in D, meaning this point is defined somewhere, either here or up here, down here. But if it's defined, well then that's when we choose M to be the max of these. If it's not defined and we just have a hole and it's not defined, well then just set the max equal to either L minus 1 or L plus 1. And we're going to let Q be this here, be this neighborhood, Q. Well, in either case, we're bounded by M, right? And M, for example, say f of x naught was up here. Well, then this is the max, so we define that as M, as absolute value of M. So then the other M would be somewhere down here. And we have that f of x is bounded. Okay, and the last thing to show that we're going to be looking at, and then we're actually done with this section, is just consider these examples. So we have f of x equal to the step function of x, which looks like that, as you can see. We have h of x equal to 1 over x. We have g of x equals to sine 1 over x. I just want to point out that each failed to have a limit at 0 for basically different reasons. Right, so this one here, why is it not continue? Have a limit because we have a jump at 0, right? So this one we didn't have a limit because it had to jump at 0. And then this one over here, h was unbounded at 0. And then g kind of just oscillated. I'll just put oscillated too badly at 0. So in a sense, these 3 examples describe the sort of behavior we may suspect of a function that doesn't have a limit at a point. Right, and we're going to comment more on this on section 2.4. This is 2.2, I believe. So in not the next lecture, but the one after that, we'll comment on this because we kind of already know what to expect for functions that don't have a limit at a point.